Hello and welcome. Today we're going to be doing an example problem for finding extrema of multivariate functions. So the example we're just going to give one example in this video. We're going to give f of x comma y is equal to z is equal to 3xy minus x cubed minus y cubed. All right, to find extrema, what we need to do is actually find critical points where the gradient vector is equal to the zero vector. All right, so we want to find those x and y points where the gradient is zero. Then we have a flat tangent plane. That's going to be a point that might be either a minima, a maxima, or it could be neither. It could be a saddle style point. All right, so to assess these things, we first have to compute grad f. So let's do it. We take the derivative with respect to x. We get 3y minus 3x squared. Likewise, we find 3x, if we take the derivative with respect to y, minus 3y squared. Like that. Right, so fx is equal to 3y minus 3x squared, and we're going to set that equal to 0. And what we get is, of course, that x squared is equal to y. So there's a whole set of points, a parabola where the x derivative is equal to 0. Now if we look at fy, we can find a similar phenomenon. What we find here is that y squared is equal to x. That's another parabola. All right, let's plot these two parabolas on a graph. There's the first parabola like that, so that's fx. All those points have fx equals 0. Likewise, this is going to be the parabola, the sideways parabola, fy is equal to 0. And we see they intersect at 2 points. The first point, of course, is 0, 0. And the second one is 1, 1. Okay. We could probably figure these out easy enough by just looking at these things. So another way to solve this, of course, is to look at points. We can clearly see that x equals 0 and 1 are points like that. But let's actually try just solving this algebraically. What we're saying here is x squared equals y and y squared equals x. Both have to be true. So that means anywhere I see a y, I can put an x in its place. So what I'm going to get is y, which is x squared, quantity squared, is equal to x. All right, so that looks pretty good. So that, of course, is going to be x to the fourth is equal to x. All right, so there's only 2 points where that can occur. That's going to be 0, and that's going to be 1, and then that's going to be -1 as well. So -1 would, well, no, sorry, that wouldn't do it. It would only be 0 and 1 that would do it, right? And of course, from here, you'd find out that y would be 0 and 1 as well. So then you just have to look at all the combinations and check them to make sure they work. Okay, so we found those 2 points. The next stage is, of course, to evaluate if 0, 0 and 1, 1 are min, max, or neither. All right, so this we have to evaluate through the second derivative test. All right, so we know the second derivative test of f at a point, we'll call it AB, is going to be equal to fxx at AB, fyy, or xab of yy, the second derivative of y, minus fxy at AB, quantity squared. All right, so let's figure this out. So we have here the gradient vector we had written as, I believe, let's go back to the previous page. Okay, we had 3y minus 3x squared, comma 3x minus 3y squared, right? So that's my fx, and this is my fy. So now fxx, of course, is going to be negative 6x. fyy is going to be negative 6y. And then fxy is going to be equal to 0. All right, so that's our... oh, no, I'm sorry. We have to undo that. Let's compute fxy. That's going to be 3y minus 3x squared. And then we're going to take the y-th derivative of it and get positive 3 out of it, right? And of course, fyx will be the same. It will also be 3 coming out of there too. Either way, you have it. Okay, so now let's put it all together. We have d of f of x comma y is going to be equal to 6 times 6, which is going to be 36. So it'll be negative 6 times x times y minus 9. So 3 squared. Okay? So this just comes from being negative 6x times negative 6y minus 3 squared right there. Okay. So with this, now all we have to do is look at the 2 points. So let's look at 0, 0. Well, let's look at that point. We plug it in, and then d of f 0, 0 is going to be equal to negative 9. So that means concave up. Okay. Oh, sorry, no. This means when we have a second derivative test of d being negative, so d in this particular case is negative, so we have neither. Neither min or max. Okay, so now let's try 1, 1. Let's try that point. And we're going to have df of 1, 1. And we're going to have 36 minus 9, which of course is a positive number. And now we have to check our point. We have to look at fxx, which is going to be negative 6. Okay, so that is negative. So this is concave down. All right, so that means that 1, 1 is a local maximum. All right, so I'd like to just sketch for you a little drawing of what this looks like. This does have a nice looking graph, pretty interesting graph. Let's see if I can do an okay job at drawing it. What we have is x, and we have y, and we have the point right here. We have 1, 1 right here, and we have 0, 0 right there. And what we have here is the surface looks a little like this. So I don't know if I'm drawing it very well, but the point here at 0, 0 is a saddle. Whereas the point at 1, 1, it's at what I call a local maximum. So I hope that helps you clear up and kind of see what the big picture is and the method of using the second derivative test. So again, when your second derivative indicator, your d value is less than 0, you know immediately it's either a min or a max, so it's what we call a saddle. However, when your d is positive, then you check that second derivative, and that tells you if it's concave down, or if in the case of that second derivative being positive, it would be concave up. But in this case, concave down means we have a maximum point. So of course this is a local max. There may be other more extreme values out there, but points in that region around 1, 1 are all smaller than it. All right, thank you very much.